Tutorial 2 question 4, you actually asked us to find the modulus of elasticity, which is your Young modulus E. Later on, he actually calculate the shear modulus, I don't know why, but I will just keep it as G first, later on we'll talk about it. And also the Poisson ratio along and across the fiber for your unidirectional laminate. So unidirectional laminate is just a laminate with fibers along this line, so it's only one direction, strong in a particular direction. So the Poisson ratio along this one is this Poisson ratio, alright, which is V12, alright, and across the fiber is the transverse Poisson ratio, which is V21. This is the major Poisson ratio, this is the minor, alright. So these are the terms that you may want to know about it. Alright, so the major Poisson ratio is the major implies that it is the major load. So the major load is over at this side, right? Because it's the strongest at this side. So the weakest is the minor Poisson ratio. Alright, and we know that the fiber weight fraction is 60%. Alright, now it's in terms of weight fraction. Later on we'll know and check it out, the other formulas that we're going to learn later on. Okay, so just take note that there is a weight fraction of 60%. So the following material combinations are these things. So there is two combinations, E-glass fiber and epoxy resin, and also the HT carbon fiber with epoxy resin. Alright, so in other words, we are calculating all this for this case and then this case separately. Alright, so you calculate this one for this case only, you calculate this one for this case only. They are not related at all. Alright, they are not related at all. I think later on in the part B they have, but we don't have part B in this question. Alright, so therefore the lecturer actually didn't go through this E-glass, because the E-glass so-called things are actually given in your portion over here. Alright, it's in terms of the density, it's in terms of these things, the whatever weibo is all over here already. Alright, so you can take note when you want to do your own stuff, because I think he will let it. He didn't do this because he wants you to actually do it your own, so that you know how to do. Alright, as for this one, he actually gives the answer for you, because this is where our materials don't have. Alright, so therefore he actually go through and provided the properties for us. Alright, because over here there is no HT carbon. Alright, so therefore I think he go through this. And therefore, in this case, alright, in this video we'll go through only this HT carbon, while the E-glass fiber I'll also let you to do it near the exams. Alright, so this is an example, same step, just different values for this one. Alright, so therefore how do you go about doing this? Okay, so therefore when you see the modulus of elasticity, Poisson ratio, or whatever shear modulus, straight away you know that you're going to talk about the rules of mixture, which is all this equations that we have seen all along in the previous tutorials. Or you can go to page 42, alright, of your reading materials. You got to see this chunk of formulas. Alright, these are the things that you want to take note of, and these are the few stuff that is very important for you, alright, all along. Alright, because you're gonna find every time when you have the rules of mixture, you need to know your volume fraction, alright, and then your Poisson ratio. These are the two things that often you need to find. Alright, volume fraction of a fiber and your Poisson ratio of a fiber and matrix. Alright, hopefully this is clear. Volume fraction of a fiber and matrix also. So this is why over here they give you the Poisson ratio of a fiber, resins, density, and modulus of elasticity. And therefore the first step, what should you do? Alright, so take a look. Alright, the fiber weight fraction, this is a new term. Alright, is not in our, we didn't go through it before. So whenever you see your weight fraction, you're going to calculate your own volume fraction. Alright, and often the volume fraction is given to you, but if they give you weight fraction, please remember weight fraction. Alright, you're going to use the volume fraction. You're going to calculate your own volume fraction. So how does the volume fraction works is that it's taking, if you remember, volume is equals to what? Volume is equals to mass over density. Or in this case, mass is proportional to weight, and therefore they actually take weight over density. Hopefully this is clear. So if you're a fiber, then uses all the fibers. That's all. Okay, actually this is like that. Okay, but however, this is only for the fiber. Alright, so there is a ratio between the fiber and the matrix, fiber and your resin. Alright, because your whole composite is including your matrix and your fibers together. So the volume fraction is the ratio between your fiber and your whole composite, and therefore you're going to include your fiber, or this is your fiber volume plus the volume of your matrix. So this is the whole composite 100%. This is only the fraction of the fiber. So if you take the ratio of it, you'll get your volume fraction of your fiber, and this will make sense and you can remember it clearer, hopefully. And therefore this is exactly what I've said just now. Okay, so this is the fraction of the fiber, this is fraction of the fiber, this is the fraction of the matrix. So you add up all together, this is the full composite, and fiber divided by the full composite will give you the volume fraction of your fiber. Hopefully this is all clear. Alright, so the volume fraction of the weighting fraction is 0.6 or 60%. Alright, so 60% is 0.6. 1 or equals to 100%, alright, is the whole composite. Okay, hopefully this is pretty clear. So your weight fraction of your composite, meaning the weight of your fiber, is 0.6. Alright, so this is why the fibers all along is this one, while the weight of the matrix is 0.4, because there is no other material, alright, because there is only fiber and matrix. So therefore if fiber is 0.6, then the rest of the weight is contributed by the resin or the matrix, therefore it's 0.4 over here. Okay, so once you know the weightage of the fiber and the matrix, you should also know the density. Or density is not provided to you, so you need to find yourself in the data sheet if they give you. So you need to know this value in the data sheet. Find it out. 1.8 grams per cm cube. Alright, while the matrix is 1.2. Or 1.2, this one is given to you from this is given to you lah, alright, in the exam. But for 1.8, I think you should need to go and find from the table. But take note that this is in terms of gram per cm cube. If you take a look from this table over here, this is in terms of a milligram per meter cube. Alright, so you need to know how to convert it to a gram per cm cube. Okay, if I'm not wrong, you no need to convert actually, because the milligram is in terms of 2.1 times 10 to the power of minus 3. So meter cube to cm cube, I think is how 10 to the power of 3, right? Because cm to meter is is 100 yeah, cm to meter is 100, so it's 100 to the power of 3, which is quite a lot. So therefore you need to multiply by 10 to the power of 6, right? Because it's 10 to the power of 2, so this is in terms of cube, so it's 10 to the power of 6. So we have 2.1 times 10 to the power of 3, which is 2110 grams per cm cube. So big, man. I don't know, I'll leave you to think about it for this case. Alright, you need to know how to convert. But in this case, we are not doing for the E-glass. We are not doing for E-glass, we are only doing for the HT carbon, which is our objective lah. Alright, and therefore it's already given to you, so you just use it now. Alright, but as for the first part, alright, because we didn't go through, we skipped the first part, since it's the same thing, exactly the same that we have been doing right now. This one I'll leave you to think about it. Alright, but nonetheless, after you calculate, you should get the value of 0.5. Alright, so these are the values that you should take note of. So what I've been doing all along is that I sub in my weight of the fiber and the density of the fiber, weight of the matrix and the density of the matrix, I calculate, then I'll get this thing. So whenever you see volume, whenever you see weight or they give you density, you should know that you're going to calculate your own volume fraction also. Okay, I repeat again, whenever they give you weight or density, please take note of calculating for the volume fraction. And therefore this is your volume fraction of your fiber. Alright, since you know that your composite is only comprises of your matrix and your fibers. Alright, so half of it is fiber, definitely the other half of it is the matrix. Straightforward. Because when you add up is 1 is equals to 1, or is equivalent to 100%. Okay? Hopefully this is all clear. And therefore once you get your volume fraction of your matrix or fibers, this I believe is pretty straightforward already. Alright? So you're gonna find your Young modulus in the one direction because they ask you to find your modulus of elasticity, alright, which is your Young modulus E, and your Poisson ratio along and across the fiber, which is the V12 and V21. So you're gonna calculate for all this, alright, which is this one, okay, and therefore I'll just plug all these formulas in, and therefore we're gonna find our Young modulus in the one direction, also in the two direction, because they are talking about the fiber along and across. So you need to know the modulus of elasticity, the Young modulus along and across the fiber. So this implies that I need to know the E1 and E2, alright, because I need to repeat in case that you forgot. This is all the fibers, this is in the one direction, this is in the two direction. Okay, so the Young modulus in the one direction is this one, Young modulus in the two direction is this one. Okay, and also the Poisson ratio V12 is actually the ratio between the compress versus the expand. So the compress is actually in the two direction, alright, so compress is in the two direction, expand is in the one direction. If it's V21, then the compress is in the one direction, expand is in the two direction. So to visually see what the hell am I talking, alright, V12 is actually compressed in the two directions. So when you pull this one, you're expanding in the one direction, right? So when you expand, this thing over here may actually go down, right? When you start to pull, if you were to have this material and if you were to pull, this part will start to tear apart, or in other words, it will start to become like that, right? Hopefully this is by realistically the case lah, okay, and therefore you're actually compressing in the two direction, alright. So same thing applies for the V21 as the minor Poisson ratio. I don't go through it, but I've been repeating all along already, so I just want to repeat again in case that you forgot or whatever that comes along, alright. Coming back here, alright, you're gonna know your volume fraction, since we know our volume fraction is this one, and the Young modulus of your fiber, you should also take note, alright, it's actually given to you, alright, not given, but it should be in your data sheet, so you should take it out as 240 GPa is your Young modulus of your fiber, okay, and also the Poisson ratio of fiber should be equals to 0.2, alright, and the matrix is 0.35, okay. It should be given to you, or it should be given over here, or it should be given in your data sheet. So the Poisson ratio of a fiber and matrix is given here, so I don't need to explain, and therefore it's just subbing in only. Alright, so when you sub in your values, you should get 122 GPa. Alright, take note that this in terms of gigapascal. So when you see your Young modulus, please in terms of gigapascal. So because sometimes matrix, right, the matrix they may give you in terms of a megapascal, because matrix is often the Young modulus is often smaller than the fiber. And why? Alright, the matrix is the lower the Young modulus, the lower the Young modulus value, the ductile it is. So you want your matrix to be ductile, or you want your fiber to be stiff. Alright, so the stiffer you are, the higher your Young modulus. That's the meaning of that. Okay, so I hope that this is very very clear. The volume fraction of your fiber and your matrix is all made known up here. Okay, straightforward. Alright, and yeah lor. So the same goes to your E1, I mean 1 over E2. Okay, so what you have will be 127. Alright, often you may straight away put in this value, don't put this. Alright, this is equals to 1 over E2. Alright, so you're gonna change. Alright, you want to find your value of E2. Alright, so this is sometimes a careless mistake that you would make. So therefore 1 divided by this is equals to 7.87 GPa. Okay, so therefore this answers your question on this one. The modulus of elasticity E along and across the fiber. Alright, so matrix, fiber, along is this one, E1, across is E2. So we have found the values of them. It's pretty straightforward already. Hopefully this is pretty clear. And therefore your Poisson ratio 1, 2. Alright, this 1, 2 is your major Poisson ratio. Please take note, major. Alright, I've explained to you in the previous parts already. So is this simply subbing in also? But take note that this is your Poisson ratio, this is the volume fraction. So Poisson ratio is actually 0.4 for your fiber. Alright, so it's 0.2. What am I talking? I look at it 0.2, then I thought 0.4. What the hell? But anyway, the matrix is 0.35 times 0.5. Alright, so just simply subbing in only, is just straightforward. You'll get 0.275. Okay, and alright, okay, wait you give me a while. So now what is V21? Alright, so since we know V12, we know E1, we know E2, then V21 is mile, right? So therefore V21 is equals to V12, which is 0.275. E2 is what? E2 is 7.87 divided by 122. Please take note that your SI unit should be consistent, gigapascal. Okay, gigapascal. So what you have for this answer is 0.0177. Okay, it's very, very, very small for the Poisson ratio. So the smaller the Poisson ratio, this means that the expansion, alright, is faster than the compression. Okay, you get me? Because for V21, right, because we are pulling in this direction, alright, so therefore this thing over here will start to bend. Alright, but if you think about it, when you pull this direction, this is the weakest part. Your fiber is arranged in this manner, so the expansion over here is going to expand faster than over here the compression. Alright, hopefully this is pretty clear. Alright, and therefore this is what it's trying to say, the Poisson ratio. So the lower Poisson ratio, the expansion is faster than the compression. So I repeat again, the expansion is faster than the compression. Okay, and this will also give you the answer for your Poisson ratio along and across the fiber for unidirectional laminate. Alright, so for unidirectional, this is the thing. Okay, so please take note of one thing. Okay, take note of what? Note that we are dealing with a unidirectional. This is unidirectional. If it's a bidirectional, alright, your Young modulus is going to divide by 2. Okay, in other words, over here at this thing over here, you're going to divide by 2, which is 61. This over here, you're going to divide by 2, which is 3 point something lah. Okay, so whenever you see it's a bidirectional, please divide your Young modulus by 2. Okay, because bidirection is in 2 direction. Alright, this is your so bidirection is arranged in this manner. Alright, for example, like that plus like that. So if you stack them up together, it's something like that. Okay, so they're equal strength in this direction and also in this direction, so they are somewhat isotropic. Alright, same strength in all directions, and therefore with this you should also know that your Young modulus should be divided by 2. Please remember. Okay, and before I go, alright, there is another thing that I will go on in this part of the video because I think it should be included, or is that if you remember, the modulus of elasticity is actually G. I'm sorry, the modulus of elasticity is E. Alright, but however, the lecturer actually calculate G also. G is for shear modulus. Alright, but I don't know why he included together with this one. But in the exam, I think you can just do it yourself. I think you can also just write it down in case it give you marks. Alright, so therefore we're going to calculate our G also. Alright, which is our G12. Okay, I repeat again, we're going to calculate for G12. So take note that we have already finished the answers, or we already acquired the answers, which is at all these steps over here. Alright, for the unidirectional. Alright, I just want to add on for the calculation for G12, which is not did not went through before. Alright, and I think also may be included because it's the lecturer, he wrote it down, so therefore you should also write it down. Alright, so we haven't finished yet. I just want you to take note that we're gonna take note of that, and therefore let's continue with what we need to do. Okay, so therefore this is the last part of this whole video. We can calculate for G12, and therefore how should you do it. Alright, and therefore this is the 4th step that we're going to be doing now. Alright, and you're going to find this is your volume fraction of a fiber and your volume fraction of a matrix. Only here this is the shear modulus of a fiber, shear modulus of the matrix, and therefore how do you find your fiber and your matrix shear modulus? Okay, simple. You're going to use this formula again. Alright, this is the one that is also provided to you in your reading material. You should know how to get this. I mean, you should know how, you should remember this one. Okay, is the more you practice, the more it will sink into you. Okay, so for the fiber, maybe I should just crop two pictures out. Okay, this is for the fiber. This is for the fiber. So the shear modulus is for the fiber for this case. So Young modulus of fiber and Poisson ratio of the fiber. Young modulus of the matrix, Poisson ratio of the matrix. Alright, so because we have all the values already, you should acquire it from your graph or from whatever data sheet that they give you. I'll not go through to you what are the values because there is no data sheet given. You should take note of all these values because it's straight away given to you. So you just plug in only lah. Your Poisson ratio of your fiber is 0.2, your Young modulus of fiber is 240. So you just plug it in and just take it out. You'll get 100 GPa. Okay. As for your matrix, alright, your shear modulus of a matrix is this. And therefore, if you were to calculate for your shear modulus of a matrix, which is 4 GPa, okay, divided by 2, 1 plus 0.35, you should get 1.5 GPa. Okay, I just copy what he written. Okay, so once you get this value, you can just sub it in only. Alright, so you have 1 over G12 is equals to 0.5 because the volume fraction is 0.5. We have known it all along at the first step already. Alright, we have calculated it using the weighting fraction. Alright, the weight fraction calculation. Alright, you should take note of how it's being calculated. Please remember that. And then divided by the shear modulus of a fiber, which is 100 GPa. Alright, plus 0.5 of the matrix volume and the shear modulus of your matrix 1.5. If you will calculate, you have 0.338 1 over GPa. Is it? Yeah, it's because your shear modulus is all at the bottom. Okay, and this is why, be careful. Alright, this is 0.338. This is not the answer yet because it's equals to 1 over G12. You want to find G12, so you're going to switch it upwards. You're going to bring this down. Okay, so therefore your G12 is equals to 1 over 0.338. This is the answer. Okay, so be careful of this fraction thing. This is often your careless mistake. So therefore 1 divided by 0.338, you will have 2.958, which is about 3 gigapascal. So this is your shear modulus in the 1-2. Alright, so shear modulus 1-2 and shear modulus 2-1 is about the same. Alright, due to stress, symmetry or whatever in elastic mechanics. So you should take note that they are the same because of some mechanics. You should go to the mechanics playlist and check it out. Alright, mechanics 4N, and then you go and search for stress, symmetry, something like that, and you can find something already. Alright, so therefore this is the whole question. Alright, as a full how the lecturers present, I present to you, and therefore this is it lah. And yeah lor, see you.